Hello and welcome to Lesson 1 of Computer Systems, National 5 Computing Science. First off, we'll look at data representation. We'll take a look at this first sentence here, describe and exemplify the use of binary to represent positive integers. We're also going to convert from binary to denary, but the vice versa we'll leave for next time. I've got a presentation for you. By the end of the presentation, you'll be able to describe binary, explain why computers use it, and you'll be able to convert binary number into a denary number. So what is binary? It's a number system. Humans like to use numbers, and the one we normally use is called decimal. The SQA like to refer to it as denary, but they mean the same thing. They're interchangeable. And what decimal means is 10 numbers. 10 numbers. We use 10 numbers. You might think it's 1 to 10, but it's 0 to 9. These are 10 numbers. And using these 10 numbers, we can create any other number. For example, this big number here, 406,105,927, that only uses the numbers that are listed here. In fact, it doesn't even use the 3. Oh, and it doesn't use the 8 either. But you can see that we can take these numbers and we can use them in any combination to make any other number. However, binary only uses 2 numbers. We don't have 0 to 9, we've got 0 to 1. And just like decimal, using binary, a computer can store any information, not just numbers actually. Everything in your computer, including the text, the graphics, anything is just binary, a 0 or a 1. So the next time you're playing Fortnite, cranking out 90s and no-scoping noobs from miles away, that's just zeros and ones flowing through your computer at incredibly high speeds. You might be wondering why computers use binary. Computers are electronic systems. It has been suggested, well, why not make a computer system that uses decimal? If you were to take electricity at a certain voltage and set it to a certain denary or decimal value, for example, if you took 1 voltage and said this is a 6, and you transfer it to another computer or even another part within the same computer, that signal can degrade. That means it slowly gets worse, or the voltage might be reduced by the time it reaches its destination. So this is a big problem. But also, what voltage would you all agree on? Would every computer agree on what the voltages would mean? This can be difficult, and there were many standardization difficulties in the early days of computers. With binary, you only need to care about 2 signals, the 1 meaning on and the 0 meaning off. With these values, degradation isn't an issue, and everyone just agrees that 1 is on and 0 is off. Modern computers contain billions of transistors. You can see a CPU down here. It contains billions of transistors, and these are just like switches, like a light switch being switched on or off, but obviously they're microscopic. In order to fit billions of them onto this chip, they need to be tiny. So now you know what binary is. How does a computer use it to represent numbers? That's what we're looking at first, numbers. Well, here's a binary number. It's a bunch of zeros and ones. And just like a denary number, each of these digits has a value. Here's 2 numbers. We've got 1 denary number, 1 decimal number, and we've got a binary number here. You can see that with decimals, you might remember this from primary school when you did tens and units. I remember that. This one has 9 units, it's got 0 tens, it's got 6 hundreds, it's got 1 thousands, and 3 10,000s. So what's the number? It's 31,609. Binary is very similar in that we have sort of values. Each of these numbers has a value. But instead of going up by tens, multiplying by 10 each time, binary numbers multiply by 2. They increase by a factor of 2. So we start with 1 on the right-hand side. We always start with 1. That's your units. And we double it. We go to 2. We double that and we go to 4. And then double to 8. Double to 16. And you may recognize these numbers. If you know anything about the history of consoles, you know that they went from, well, they kind of started at 4-bit and then to 8-bit, 16. And then 32, 64, 128, and so on and so forth. And you can probably figure out that this number on the bottom is made up of 1 8, a 2, and a 1. But what does that mean? Well, we add up all the values that have a 1 underneath. So the 8 plus the 2 plus the 1, that makes 11. So 11 in binary is 0, 1, 0, 1, 1. Here's another example. We have 1, 0, 1, 1, 0. What does that mean? Well, we take the numbers that have a 1 underneath it and we add them together. 22. Here's another example. What does that mean? Well, first we need the binary values, and the values that have a 1 underneath it, we add them together. There we go, 55. Another example. Get the binary values above each digit. Remember, starting at 1, doubling each time. And add the values that have a 1 underneath. 29 for this one. What about this one? Oh, that's lots of digits. Well, you could put out all the binary values and add up all the numbers that have a 1 underneath, but you can see that it's just the 4. And you wouldn't even need the values. You can just go, oh, that's a 1, that's a 2. This one must be a 4. So this whole number, it's just a 4. This type of question comes up every single year in an exam, converting binary into denary. You give this a go, see if you've learned how to do this. I hope you've enjoyed this lesson. Hopefully you can describe binary, explain why computers use it, and you'll be able to convert binary numbers into decimal or denary. I'll see you in the next one.